Hello, everyone. Thank you for joining. This is the third part of our webinar series. Please feel free to use the chat channel to interact with others in the webinar. We have 4 leaders with us who would be helping you out on the Slack channel too. So I'm just going to have these links up for a quick second so that anyone who wants to join can take quick screenshots or make a copy of the links or the QR codes. And we will also be sharing the links on the chat. So anytime I mention any links, please keep an eye on the chat so that one of our leaders will reach out to you with the links that I'm mentioning. Helena has just sent the links to us. So I'm just going to start this off. So these are the actual links which are there on our Slack channel, on our chat channel. So please use that to join our community. Where we have like online presence on our website as well as on Slack, Twitter, Instagram, and YouTube. The YouTube link is not here, but you can quickly search it up, and there is a Women Who Code YouTube, which contains videos from all chapters and all tracks. Yes, we will share the links for the Colab notebook and everything shortly. Just some housekeeping before we get to the webinar. Next thing, we want to thank our sponsors, Home Depot, for helping us put together these events. These webinars are definitely very much needed right now with the current situation, and we're super grateful that we have a big company such as Home Depot on our side helping us put together these events. So coming back to the bootcamp, this is the data science bootcamp. We're on the third part of it, third and final part of it. We have 4 leaders joined with us, including myself. I'm Sumana Ravikrishnan. I'm a data scientist at ServiceNow, and I live in California. And I'm here to share, lead the session and share more information about things I've learned in the field of data science. We also have Helena Baumer, Deepika, and Anju joined with us, and they'll be super active on the chat channel. And you can reach out to them if you have any specific questions or anything at all, but please use the chat channel to network with the panelists as well as everyone who's part of the webinar. And if you've missed part 1 and 2 and you're just joining us for part 3, don't worry, we have recordings of all the sessions till now, plus additional recordings too. So part 1 and part 2 are present, and the links present here. You can find the links on the chat channel too. We also have an extra video on how to link Google Drive to Google Colab, since a lot of you faced issues with it last session. So you can use these 3 links to catch up, and the recording from this session will be available by Monday, and we will update you on Slack with that information. So please join us on Slack. And yes, welcome to the third and final part of our mini data science bootcamp. As I said, I'm Sumana Ravikrishnan, and I'll be running this session and walking you through how to create and compare machine learning models. So one thing to note is any important links that I mentioned during the webinar, please keep an eye on the channel. One of our leaders, on the chat channel, one of our leaders will post all the links that I'm mentioning by word so that you have access and you can directly click and go to the links that I'm mentioning. Also, if you do have any links that are useful from your end, which you found useful in your data science learning process, please feel free to share that too on the chat channel so that everyone else in the webinar can benefit from that. If you have any questions during the course of the webinar, please use our Q&A channel to post your questions. It gives option for participants to upvote or downvote a question. So if you feel that a question has already been asked and you would like the answer to it, please press an upvote on it. Our leaders are going to be monitoring the Q&A channel to the max, and you should be getting responses immediately. And if any of the questions catches my eye during the webinar, I'll pause and make sure that I answer the question live during the webinar. Awesome. And getting to the main nitty-gritty of the session. So this is the link to the notebook. You can use it to open up the notebook on your local machine. Once you do, open it and save a copy to your drive, because this file cannot be edited by you and the cells cannot be run by you. And so I'm just going to go over to the notebook now. Once you open the notebook, the link should open up this link for you. The link is also present in our chat channel. You can use that to open up the notebook. Once you get to the notebook, go to File. Oops, I pressed Edit. File, save a copy in Drive. And that should create an exact copy of this in your local drive, which you can run and edit yourself. Right now, when you try to run anything in this, it would say that it's in read-only mode and the kernel is not connected. So make sure you make a copy of it. And I'm just going to give you guys a quick second before we jump into this so that you can make a copy of these, of the notebook. So before that, I just want to quickly go over what to expect out of this session. What are we going to cover? What are we not going to cover mainly? And what next, pretty much. So in this session, we're going to look at creating and comparing ML models. Till now, we've seen how to clean our data, produce statistics on our data, and visualize the data standalone. So now we want to see if we can put together the things that we just learned to make inferential decisions on our data and feed that data into our model. So for that, we're breaking this up into 2 supervised machine learning models that we're going to take a look at, which are classification and regression. And we've randomly picked 3 different machine learning models within these 2 classes, which achieve classification and regression for us to use. And we will be going through that shortly. But the main points that we would go through in this session is how to do feature selection and engineering using the skills that we just learned, such as cleaning, stats, and visualization. What are performance measures? How do you know if your machine learning model is doing well or not? Next up, we create the model themselves. And then we try to extract results from these models to understand how well or badly they're doing. And once we know how well or badly we're doing and we have a comparison metric, we can then pick which one works best for your use case. So these are the 5 main topics we'll be touching. And the 2 main machine learning model classes that we're going to hit upon are classification and regression. Classification is when the output variable or we're trying to predict is a nominal field, such as yes, no, or black, green, white. Say I have a database which has the color of balls in a given bag, and the possible variables are green, black, and blue. Green, black, and blue are a categorical variable in nature and not numerical in nature. So this is considered a classification. Predict what class is the right one. Regression one is when the output variable is numerical in value. So if I have a data set with the heights of people and the corresponding ages of people in a given county, using that, I can predict, hey, in the past, I've seen that so many people of the age 40 are 5 feet in height. Being able to get a relationship between the input variable, which would be the age, and the output variable, which would be the height. And being able to predict for a new person, given the age, I know what height that they would be. This is a very bare bones and bad example, but it's the simplest example that I can think of. So classification is when we're predicting a class. Regression is when we're predicting a precise number. So there's more information in this link over here. If you check it out, it just gives you a description of machine learning in general, what the different classes of problems in machine learning are, and how to achieve what you want within them. So I highly recommend this for starters of machine learning to get an understanding and a feeler of what to expect and what is in machine learning pretty much. So one thing to note is that this notebook will go over the black box of what a machine learning model is. We are not going to learn what happens inside the model, what math is going on behind the box, what kind of formulas are being applied, but we know that we have a model in hand and we're going to treat it as a black box where I'm going to give it input and I expect it to give me a prediction. So we're putting together another course, a 6-week series starting in mid-May for Introduction to Machine Learning, where we will dive into what each machine learning is doing mathematically and try to get an understanding on that. So that series would give you a more in-depth explanation of models, what they are, what kind of math is going on behind it. Because machine learning, I feel, is a lot of math. A lot goes on behind the box, and we are and has been abstracted away, and we are not seeing it happening, so we don't know what's happening behind the box. So if you're interested in that, please keep an eye out on our Slack channel. We will be having a series starting in mid-May, and we'll post information about that soon. For those who don't have time to wait till then, another great free online course for machine learning is by Andrew NG, is there on Coursera. I don't know why this thing is happening. Yeah, let me pull this back up. Okay. Another great free online course is the one on Coursera by Andrew Ng. And that is one which I personally use to learn a lot of concepts in machine learning, and it helped me a lot, and I highly recommend it. This course starts on April 13th. It's a free course. It's coming up in 3 days. And if anyone wants to kickstart their data science learning process and machine learning process, this would be a great starting point for you. So please do take a look at this. I think the link should be there on the chat channel. Please do register if you do have the time and would like to learn more about it. Okay, so this is a general idea on what we're going to be covering in this session. So let's jump in and start off. First thing that we need is, as always, we need our data sets. So in this case, we're going to be using 2 data sets, which is the Boston housing data set and the IRIS data set. If you take a look at the links that are provided in this, you can see what each column is, what the data inside that column means, and more information on how many rows and columns to expect in the data, and so on. The good thing about Kaggle is you can always go to the discussion thread, and a lot of people are working on the same data sets that you're working on. So you can check out the discussion thread to see what kind of projects are people doing. Are they doing anything cool? Would you like to do something like that, and so on. But moving on, enough about Kaggle. But yeah, those links will get you information on what each column means, since the column names are very coded very well, and won't give us an idea from just looking at it on what the name is. So moving back to the notebook. So there are 2 data sets in question. Both data sets have their own type of data in it. The links to this will give you more information on what kind of data is stored. But the best way to go about it is to actually see the data yourself. So the first cell that we're going to run would basically import all the packages we need for pulling our data, running the models, getting accuracy metrics, and everything involved. So don't feel shocked that there are so many lines of import that are happening here. But these are just necessary because we're using a lot of models in this case. So let me make this a little smaller. Perfect. So first cell, we're going to pull the IRIS data set. So if we take a look at this, datasets is an existing package that we have already imported. And they come with existing functionalities such as load IRIS, load Boston, and so on, which basically loads the data set into Pandas. And once you do that into Python, and then once you do that, you convert this raw data into a data frame using the following process. And then we're just visualizing the data to see what happens. A quick refresher on how to run cells here. You can hit the play button, or you can hit shift return or shift enter based on what OS you're using or what machine you're using. And that should basically run your cell. So in this case, we see that iris.shape is printing this, which is number of rows, comma, number of columns. So printing .shape of a data frame would give you that. And I'm just doing a head of 5 to just get a sample of the first 5 rows in the data set to get an idea of what kind of values are sitting in them. Are they numerical in nature? Are they categorical in nature? So that I know how to handle them in the future. So in this case, the IRIS data set has 5 columns. The 5 columns are sepal length and sepal width, petal length and petal width, and what species they belong to. So I'm just going to pull up the IRIS dataset documentation right here and give you a quick idea on what is in the data itself. So we have all of these columns. So as far as species go, these are the possible species that are present in the column. So they've already done their own data visualization on the data to understand what's going on. So the good thing with public data sets is a lot of people have already done a lot of stats generation, visualization on this data. And a good point would be to see if anyone else has any questions, anyone else has any like inferences they've made on the data or any questions on the data. You have access to this and you can take a look at this. But without doing any data modeling ourselves, we can quickly take a look at what kind of data can we expect. So the species is either setosa or versicolor. And we have a varying length of numerical inputs for sepal length, width, petal length, and width. So moving back to our notebook. So let me scroll down here. So this is a sample of the data that we have. So it seems like the species is coded to be a number. So even though this has a number in it, it actually in the end means 0 is a given type of species, 1 is a given type of species, and so on. So that's a very important thing to note. Even if the data set contains numbers in them, those numbers may not have a numerical meaning in them, but have a categorical meaning for them. So it's very important to understand your data before you go ahead and start doing any cleaning, visualization, or generate any statistics on it. So based on this input, iris data, I know it has 4 numerical columns and 1 categorical column species. And yeah, that gives you a good idea on your data set. We're going to do the same with our Boston data set, extract the data using load Boston, put it in your data frame. And we're going to see what all columns we have over here. Seems like all of them seem to be numerical in nature from first glance, but we need to take a look to make sure that what we understand as numerical isn't numerical actually. So we have 14 columns here, 506 rows. Of the 14 columns, let's take a quick look to see if any are categorical in nature. So this is per capita crime rate per town, numerical proportion of residential, numerical proportion, numerical. This is dummy variable, 0 if otherwise, 1 if it's bounds a river. So clearly this value is categorical in nature and not numerical in nature. So you would need to treat it as a categorical variable over a numerical variable. And then quickly going over the other columns, concentration levels, it's numerical, number of rooms, numerical, proportion is numerical, weighted mean numerical, index of accessibility, that's also numerical. Actually, index of accessibility to radial highways, that will be something for us to check to see if there's only a small subset of variables that are there. Is it a value that ranges from one value to another only? Are there multiple rows with the same value in it, and so on? So tax, so RAD is something that we want to confirm if it is numerical in nature or categorical in nature. So tax is property tax rate per 10,000, numerical pupil teacher ratio, numerical proportion of blacks by town, numerical lower status of population is numerical percentage, and median value is numerical too. So from this, we can see that everything seems to be numerical other than the CHAS one. So this is categorical in nature for sure, we know about it. And RAD might be categorical or numerical, we're not sure. Otherwise, everything seems to be numerical in nature. So moving back to our notebook, we've successfully loaded our data sets into our Google Colab notebook, which is the iris data set and the Boston data set. Both my data sets are in the variables Boston for the Boston data set and iris for the iris data set. Makes it easier if you name it well. Okay, awesome. So our first starting point is done and checked off. We have the data now in the Google Colab notebooks, so we can start like manipulating it, visualizing it, creating stats on it, and then finally build the model on it. But one thing to note before doing all of that is we need to split our data. Why is it important to split our data? So first thing that you need to understand is a machine learning model, it doesn't do anything fancy. It does what you think a human would do. Say I have a bag with 50 white balls and 50 black balls, and I get to like take a look at it, go through it, understand how the data is varying in it, how many balls are there, and so on. And then now I'm given a bag which has, which is fully blocked out with 10 balls in it. And I'm supposed to make an inference on how many balls are going to be white and black in that new basket. So from my inference in the old basket, I learned that 50% of them were black and 50% of them were white. Based on that learning, I'm going to predict that the new basket has 50% black, 50% white balls. In this case, 5 black and 5 white balls out of the 10 balls that are there in the new bag. So this is what a machine learning model does. So say that I have a data. It tries to look through your data, make a lot of inferences on your data, and then given new data, it uses the inferences that it gained from the first data set and applies it on the second data set. So one thing to note here is, say I want to make a prediction on the iris data set, given the sepal length, width, petal length, width, being able to predict the species. And say I have a data set with 200 rows in it, and I'm creating a model on this. So my model goes through and sees what combinations of sepal length width, petal length width make up a given species, and generates a formula that this species is going to fit into this formula, this species is going to fit into this formula, and so on. So say that I have a flower which I want to predict, and I get, and this flower is part of my iris data set. So that means that my model already knows what I want to predict in the model itself, and then uses that to make the prediction. So that's like a form of cheating, where you know the answer before itself, you learn from the known answer, and then you try to make the answer out of a known answer, right? So in that case, we don't want this level of cheating at all. And splitting your data removes any form of cheating that you can do with a machine learning model. So in this case, 80-20 split is what is usually used. We need to split our data set into a training data set, which is used to like make inferences, build models, and the data set that you can view, and view and analyze. And then we'll have a testing data set, which you haven't viewed at all. You have no idea what is in that data set at all, and you're fully blinded to the content of this data set. So our goal is to create a training data set 80%, build a model on this, and use that model to predict the 20% that's remaining to see if it's a good model or not. So what happens if this 20% is already present in the model that I'm building? So that would be cheating, because the model is now learning from the 20% it's not supposed to see. And then it's making predictions on that data, even though it learned from that data already. So that is the thing we try to avoid here. And splitting your data avoids cheating in general. So, so the main thing to note is we create a model on 80% of the data with no knowledge on the 20%, and see if the hypothesis we formulate on the 80% of the data can be generalized for the entire data set. So that is the goal that we're trying to achieve. So it's very important to split your data, or your model will be cheating. So Python has its inbuilt packages which does splitting for us. And this cell here basically does that. Model selection dot train test split basically splits your data. The parameter is your data set, and what the size of your test data is. So train data is always going to be test data 1 minus test data. So in this case, my test is going to be 20% and my train is going to be 80%. So, and this function basically gives out two data sets, which would be the 80% data set and the 20% data set that we load in train and test. So I'm just going to run the cell to show you what to expect. So the iris data set has 150 rows. Then after splitting it into train and test, we see the train has the first 120 rows and test has 30 rows. So, so this is very important to split your data, and easiest way to split your data. So I'm going to do the same for the Boston data set, get an 80-20 split, total 506 rows, of which 404 are the training data and 102 are for testing. So now that we understood how important it is to split your data, and also how important it is to not cheat, we split the data successfully, and we move on to the fun part that we learned till now. Okay, I'm just going to answer some questions from the Q&A chat. So this question is about train test splits linearly or randomly splits the data by setup. So this functionality does randomly, but you can look it up online and see how to make it force and take it in order, because it's very dependent on the type of data set I have. So say I have a time series data which has chats from a person starting from Jan to April. I want to use Jan to March to train my model and predict for April. Using a randomized thing in that case will not be useful at all. So in that case, it's very important. So it depends on the use case you have, whether randomizing is a good thing or a bad thing, and if there's any time component involved. Answering Olga's question, when you have a validation data set addition to testing data, is it necessary to predict which both testing and validation data set? So Olga, I think your question, your meaning, you've seen like the concept of validation data sets online, where people split their data into a 70-20-10 split, where 70% you train your model, 20% you use as your testing data, and 10% is validation data. So in the case when you're building a machine learning project, you always try out multiple different models to see which one works best for your use case. So the reason why the 3 split is happening in this case is you get an idea on what your test data is because of how many iterations you run on your training. So I can build 10 different models on my training, do it on the test, and then I'll get an idea on what works well for my test, and I end up tuning my model because I know what's there in test. So this extra additional validation data set removes that level of cheating also and makes your model quality better. Perfect. And what is the essence of resetting index? Adiola, I'm not sure if any reset index is happening here yet. But one thing is, actually, let me answer live. So the reset index is used to reset this column over here. So an index comes inherently with Pandas data frames. And in this case, it always goes from 0 to n-1. And there are cases where your data set could have been saved in a way where it's been sorted and the index has changed. So in this case, if I sort this data set, my index would become, say, this is sorted in ascending order, and I do a descending order sort. My indexes will become 4, 3, 2, 1, 0. So to avoid any confusion in this index over the data, we do a reset index so that we know for sure the index goes from 0 to n-1, instead of having to deal with that later. And next question is, when we need to apply resampling methods, I mean, you're talking about trains test, but that will not be enough. That is very true, Patricia. And it also, again, depends on the data set that you're using, the use case that you're working on, and so on. Resampling is useful in some cases and not useful in a lot of cases too. Resampling can be useful when your data set is skewed and all of that fun stuff, but it's very dependent on the data itself. That's why, like, data science in general requires a lot of experience, because you learn a lot from previous mistakes and so on. So resampling methods, yes, we will need to apply them based on our data. That would come in after analyzing your data, finding out if resampling is required. Resampling mainly is required if the data is skewed, if there's like a concentration of data in some specific class and so on. So it's very dependent on the data. And like I mentioned in the first thing, in the beginning, we are not focusing on what happens in the black box. We are just focusing on how to mold our data to get into that black box. And we'll be focusing on resampling methods and all of that fun stuff in the next series. So please keep your eyes out for that. And answering the last question I see here, which is Lisa, not by default included in the data columns. Yes, you are right. So the data, so if you see type of the Boston raw, I'm just going to like quickly add a cell here and show you that the data type is different. And that is the reason that this is happening. So if you see Boston raw, I'm not expecting Boston raw data set to have type of Pandas data frame. See, so the data type itself is bunch, and this is the way that the data is stored in the bunch data. So it's not a Pandas data frame, and do not get confused on why it's being handled differently. Perfect. And yes, so I think I got all the questions. Moving on to our favorite bit, which we've been training for till now, which is our feature selection and engineering. I'm just going to zoom in a bit so you get a good view on this. Perfect. Okay. So feature selection is very important because of this problem that we've been facing for many years, which is the curse of dimensionality. So one thing we assume as humans is the more information you have, the better your understanding is going to be. But this doesn't work as the case for machine learning models, because some of the data that you're providing could be considered as noise, and this could be like degrading the quality of your model in general. So say in the case where we have the Boston data set with 14 different columns, and we're going to predict one of the columns. So it has 13 different columns that can be input to the model. I don't want to provide all 13 columns because one of these columns could be like skewing up my results completely. And that is a general problem that we face in machine learning. More data isn't better, quality data is better. So that's why feature selection is a very important step. You need to make sure that your data has like really good quality, or else how much ever data you provide, it's not going to make a difference to your model. It's going to be a bad model without fail. So it's very important to do feature engineering just to get rid of this curse of dimensionality problem. There's a link here which tells us more on what curse of dimensionality is, what are the general processes used, and so on. So please do take a look at that and see what's going on with this. So one main thing to note, based on our cheating example that I gave you before, we will conduct this analysis only on training data. We are not allowed to touch the testing data for feature engineering, anything at all, even to understand like how many rows are there. It's illegal to touch it. So that's one main important point of machine learning. Once you have your testing data separate, you do not get to touch it at all. You do not get to see into it or peek into it or anything of that sort. So this is going to happen only on our training data. We're going to set up some feature engineering and so on, and let's take a look at what is going on. I'm just going to answer Catherine's question. Are you going to do feature scaling or mean normalization? Are there built-in methods to do this, or do you do them by hand? So there are, for most of the things that you want to do with your data, there are definitely built-in functions that are present from Python or Pandas or sklearn, even NumPy. So I would definitely encourage you to see if what you're trying to achieve is already present online, already present as a package, and to use that because it's been standardized and tested, rather than writing up the code yourself. And yeah, that's pretty much it. We are not going to be doing any like big feature scaling, mean normalization, and all of that fun stuff. We'll be doing a little bit of feature engineering just to give you an idea on what feature engineering means, how to go about it, and so on. And we have links to like online resources for you to check out on what different types of features you can generate and all of that fun stuff. So yeah, this is just a starting point for you to get started with this process. Perfect. Moving on. So the first feature engineering method we're going to see is null handling. Anju touched upon it in our last session where we saw a bunch of nulls in our data, and a lot of you had questions on how do we handle null data? What are we supposed to do? Like, what is the best case scenario to do this? So the first thing I want to do is to see if any of my columns have null values in my data set. And if it does only, we need to worry about null handling, else we can just ignore it. So the first thing I do is iris train, which is our training data. Do not touch the test data, as I said before. Is null basically generates how many null values are present per column. And then a sum is doing a column-wise addition on this. So in this case, seems like none of our columns have any null values in it. So no null handling is needed in the iris data set. And similarly, the Boston train data set, also same thing. We do not have any null values in it. So no kind of handling needs to be done. So one thing that Anju mentioned in the previous session, which I want to like reiterate, is as far as null handling goes, there are multiple different ways for you to handle it. A couple of things are, you can just impute the mean. Like, it depends on the data set that you're working with. Say I have a categorical column, yes or no, in which has multiple null values in it. You need to first decide, is most of it null? Do you want to discard the column itself completely? If most of it is null, discard it because it's not adding any use to your data, and it's just going to be adding noise and adding to our curse of dimensionality. Second thing to note is if it's based on whether it's categorical or numerical in nature, the way you handle it will differ. First thing is, if it's categorical in nature and you find a subset of say 20% of your data has null values in it, a couple of things you can do to impute the null value is to see which is the most popular class in your data and put that as the value there. So say I have yes and no, 90% of my data is yes, 10% of my data is no, 20% of my data doesn't have any values in it, it's null. So in that case, I would be filling up all the nulls over there with yes, because it's the most popular value. So one more thing to note is, if that doesn't turn out well, if that's not a good way based on the data that you have, one cool thing that you can do is you can build a model which predicts the categorical value for the ones that are missing, and then build a model on top of that which takes that categorical value as input and builds another model. So there are different ways to handle it, and it's very, very data subjective. It completely depends on what kind of data you have, what the data means, and you cannot apply anything directly based on just, hey, it's a categorical column and there are missing values, blindly apply this. So that's not a thing when it comes to this. A lot of experience is needed, and a lot of understanding of your data set is definitely needed. Okay, I see a question here. What is the difference between scaling and normalization, and why would you pick one over the other? So scaling and normalization are different concepts. Normalization is basically bringing your data into a constrained value, and your value would say always exists between 0 and 1. Why would normalization be good? In this case, say I have a data set with a lot of numerical values starting from 0 to 3 million. Like those in the 0 value are going to be diluted because of the high value that's there in the data points which have 3 million in them. So we need to normalize our data so that it exists in a range of 0 to 1 rather than 0 to 3 million, which will just increase the range of our data, increase like what the values mean and so on. So to make sure that all the rows in your table are of the same format, say I have one row where my data point is of value 1 and one row where my data point is of value 3 million, this will affect your model internally and give a different understanding for what 3 million and 1 means and dilute out the value of 1. So normalization is very important for that. And scaling comes in a different way where you need to scale, where you have control on what the scale of your normalization is. And again, to answer that, answer why I would pick one over the other is it's completely dependent on the data. You cannot make any decisions or in machine learning without taking a look at the data. So moving back to our null value handling, as we see here, there are no null values to handle. There are multiple ways in which you can handle it by imputing values or removing the rows where null is present. It completely depends on the data that you're working with. So we're going to take a quick peek into the Boston data set. And we have the describe function, which we mentioned in our last session. Describe basically gives the statistical values on each column of your data set. The stats that we're producing are count, mean, standard deviation, min, 25 percentile, 50 percentile, which would be median, 75 percentile, and max. So you know like what range your data sits in and how the distribution of this data is. Is it a normal distribution and so on? So, like one thing after running this is to just get an idea on each column, understand like if the range is too big, range is too small, and so on. So one main inference that we are pulling up in this notebook is the tax column has a minimum value of 187 and ranges till 711, which seems to be a very big gap. So I want to do like feature scaling to fit it between 0 and 1. So that like this value isn't like pushing my data to, pushing my model to do badly. So we're using an existing functionality called min-max scaler. And what I'm going to do is I'm going to pass this data, which is only the column I want to do the scaling on, to the function. And this would change the data that's present in the column. So what I'm going to do is I'm going to print what the range of the column is before I do scaling, what the range of the column is after I do scaling, just to make sure that the scaling has applied. And once I do that, the new column, I'm going to append it back into my database as tax scaled, so that we have both the tax column and tax scale column. And during model creation, we can try out using both as input separately to see if one is doing better than the other, just to get an idea on how a small change in the feature engineering is going to affect your results very big. So running this, our range, as we saw before, is 187 to 711. Now I've reduced it into 0 and 1. And we're going to append this back into our trained data. So I'm just concatenating the scaled column back into our trained data. And I'm going to concatenate it by axis equal to 1, which is a column-wise concatenation since I'm adding a column. And I'm using the index to join the axis. So then if we see this, what's happening? Join axis is wrong. I don't know why that's the case. But in this case, this is the thing. So answering your question, Adiola, it depends on what your data is. Right now, I've just picked one randomly, which has like a bigger scale, a difference between the min and max, and showed how you can reduce it to a smaller one. you can definitely take a look and see if any other of these columns seem a little wonky and you would require scaling or anything of that sort to be done to that column. So this one has been specifically picked at random because I felt it was a very big range, but there is definitely scope for improvement over here. There are other columns too, like none of them have like such a big difference between min and max actually, to be honest. So yeah, it completely depends on the data set. Answering Dawn's question, yes, yes, they should be reflected in the count. Let me just move back to the output we saw here. Say I have 3 null values in the column sepal length. This value would reflect 3. So in this case, I'm just going to break this down to teach you, to make you understand what's going on. So iris train is all the columns. Is null is basically taking your entire data set. Say I have a data set in this case of 5 rows and 10 columns. It's going to take that entirely, check each cell and mark it with a true or false based on if an is null value is gotten. So now we have a big database which has true or false values inside on whether the value is null or not. Dot sum just basically does a column wise addition of the true values, and that would add up the true where the true is null and add them up to the values here. So yes, to answer your question, the count will be affected by, the sum will be affected by a null, count will not be affected by null value. Okay, moving back to our scaling, we concatenated the scaled data back. So there are some exercise sections that are present in this notebook. You can just search for exercise to see what's happening. So the exercises, are there any new meaningful features you can generate from existing features in Boston or Iris datasets? So I would suggest if you have a copy of the notebook, add the exercise sections when you're running this on your own. You can just add a code block there and try out whatever you would like to try out right there. So I'm just quickly showing you how to go about running these exercise sections. Okay, so moving on, we saw a quick example of how to do null handling, even though we didn't have any nulls. A great example of how to do scaling, feature scaling, which is basically normalizing your data from 0 to 1. And then we are moving on to the feature selection part of it. So as far as the feature selection goes, we're now focusing on, this notebook will focus on running things for the Boston dataset. And we encourage you guys to try out something similar with the Iris dataset so that you have an understanding of how to deal with new datasets on their own. So as far as feature selection goes, this again comes back to the curse of dimensionality. Say I have 10 columns in my dataset and I want to predict one of them. 9 of my input columns, if I provide all 9 input columns, that doesn't necessarily mean that the model will be better than providing only 8 columns, 7 columns, 6 columns, and so on. So the quality of the model doesn't depend on how much data goes in, but on the quality of the data itself. So if you feel one of your columns quality is low, that means you can easily just drop it. So how do we define quality? So in this case, quality is defined by how related is your given column to the column you would like to predict. So in this case, I'm going to see if, like, what is the correlation between every column to every other column? Is there like some existing similarity that's present, which I'm missing out, and how to go about it? Adiola, if you had seen what I was doing in the webinar, just remove that extra parameter, which is join axis, which is there. I think the kernel on which the Python is running doesn't have that functionality present. If we just remove the join axis parameter, this should work fine. So moving back to this, yeah. So we want to see how each column is related to each column. If 2 columns are like super similar and have very similar values in it, providing both the columns to your model isn't going to make it better. Just one of them will be good enough. So this is to get an understanding on how each column is related to another and to pick which column do we want to predict. If we're predicting that column, these columns are not useful, so we need to drop them. So we're going to do this with the help of a heat map. A correlation value is based on similarity. So you can either have, so the values range from -1 to 1. -1 meaning high negative correlation between 2 variables, and positive meaning high positive correlation between 2 variables. And anything in the middle or around the middle with 0 values show no or very low correlation with a given value. So in this case, if you see on the right, we have a chart showing what color codes they are. So the lighter ones show high positive correlation, darker one shows high negative correlation, and everything in the middle shows low correlation in general. So with respect to the Boston data set, we're going to pick MEDV as the column we're going to predict. Oh, I hate this. Yeah. MEDV as the column we're going to predict. And we want to pick a bunch of features from the rest of the columns that are there to see which ones would make sense to be inputted into our model. So in this case, this code, the heat map generates a heat map where the rows and columns are the columns from your data set. So we have crime till tax scaled on both the axes. And each of them have a color coded value based on the correlation value themselves. So one thing to note is we want to pick the most correlated ones. Most correlated is defined by being closer to -1 or 1. And we want like a high negative or high positive correlation variables to be added to this. So in this case, we have so many input columns, and I want to pick something that's a little less in number, pretty much. Pick up something that's little less intensive on the model. So for this exercise, I've decided I'm going to cap the number of features that I have at 4 and pick up only 4 features that are useful. So this isn't a usual process you use while building actual models in production and so on. This is just a case for me to show you how this works. So this is just to show you that I am trying to reduce the data. In real life, you wouldn't be picking a number saying 4 is the good number of features or 5 is the good number of features. It completely depends on the quality of your data. So in this case, I'm just decided I'm going to pick 4 to just show you guys how it works. So I'm just going to print the correlation matrix of MEDV, and I'm going to sort them so that I have like high positive correlation up top. And running this, oh, I didn't run this cell. So let me run this cell and then come back to this one. Yeah. So we see MEDV obviously has 1 as the correlation because the values are exactly the same. So we can ignore that. The next one we see is RM, which has a 72% correlation. That seems like a good number. ZN has a 40% correlation, and so on. And as far as the negative correlation goes, we see LSTAT has a negative correlation of 75%. That's really good. And PT ratio has a negative correlation of 60%. That's also really good. So for this use case, I'm just going to go ahead and pick 2 from the positive correlation, 2 of the most positive correlated columns and 2 of the most negative correlated columns. This isn't how it happens in production, and you would have to actually do more experiments on it. But in this case, I've decided let's just pick the ones with 2 high positive correlation, RM and ZN, which is above 40%, which is good. And negative correlation, we have PT ratio and Indus, which we're going to pick. And moving on. So I've decided to pick these, and we move on to the data pipeline section. So there's a small exercise over here. Since we did the same feature selection for the Boston data set, see if you can replicate it on your Iris data set. Iris will definitely be easier for you to work with, since the number of columns that you have is only 5, where 4 are going to be input columns and 1 is going to be an output. So it's very important to make sure that all these 4 columns are of good quality, have high correlation, and are going to help your model, rather than throwing noise into the model and degrading the quality of results. So next thing to do is data pipeline. So setup, Indus or LSTAT. It seems like I've picked Indus for this one. Let me just confirm. Yeah, it seems like I've picked Indus for this, but technically it should be LSTAT and PT ratio. I don't know if that's a typo or if that is the one I ended up picking. We'll get to know that in a quick question. I'm just going to leave your question up so that we can answer it when we get to the model building section. So yeah, moving back to our data pipeline. So now that you know that, hey, from the Boston example that we saw, at least, we know that we're going to pick only 4 ones, which are going to be 2 highly positive correlated ones, 2 highly negative correlated ones. You need to set this up as a function so that you can run your testing data through the same model too, without actually peeking into the data, because it's very important you don't see your data. So all I'm doing is I'm going to take a given, I've defined a function called scale column, and which takes your data frame as input and which column you would like to scale. And whatever we saw right now, I just threw that into a function. Nothing fancy is happening. And I'm returning a new data frame which has the underscore scaled added to it. So in this case, we already have a Boston train data with tag scaled as added as the additional column. So we want to run the same process on our test data too, but not taking a look at our test data pretty much, and not having to do it manually. So Boston test.scale column, it's going to run it on this. So I'm just going to do a range before scaling and range after scaling. I'm going to print. Oops, sorry. Range after scaling, and column name plus scale will be my new column. Yeah, perfect. So that it prints out both, and I'm not going to print the head of my Boston because I don't want to look at my data. So Boston test, oh, this is the same thing. I don't know why, but join access is not being accepted as a parameter. So everyone who's using this notebook, make sure for the pd.concat to remove join access from the function. I think it's been deprecated. So moving back to this, we see, oh my God, what is happening? Okay, let me just move back to how this was. Seems to be changing up what I'm doing in this data. Okay, so in this case, our tax column has so-and-so values. Our tax scale value has so-and-so values. So the values have been changed internally. It seems to be existing within the range of 0 to 1, which is a good thing. And from that, seems like 666 is the biggest value present in tax. So this is why I don't want to visualize this test data, because you end up peeking into the data and making inferences internally yourself. But yeah, so any function you try out on your trained data and it ends up being successful and it's in the way that you want your data set, make sure you put it in a function so that you can pass your test data through it too, to ensure that your training data and test data have the same data processing pipeline applied on them and haven't been diverged in that way. So any other data operations you've been doing on your training data, the exercise would be to generalize that and throw it in a function so that you can apply the same on your test data. So there are two new terms I would like to teach you in this. One is features and one is labels. So machine learning models will extensively use these two values or use these two names in them. Features are going to be whatever you're inputting to your model as the input that it needs to learn from. Label is going to be your expected output from the table. So I'm going to just explain this quickly with our iris dataset. So iris dataset we saw has 5 columns, of which 4 are petal length and width, sepal length and width, and we have the species column. So from this case, I'm going to make species my label because that is what I want to predict. And my features are going to be petal length width, sepal length width. So those would be the features and label for this data set. So now we already have split our data vertically with train and test. Now we want to do a horizontal split on which are the input columns and which are the output columns. So we have train and test. Now I'm going to be splitting that into train features, train label, test features, and test label. So we're going to split this into 4 data sets because this is the input our machine learning model expects the data to be in. So let's just do the same with the iris data set. So all I'm doing is I'm specifically saying that these are going to be the features, the 4 columns that I just told you, and species is going to be the label. So I'm just going to print out what the labels and features are. And then the train data, I'm going to be splitting into underscore features and underscore label, the parameter that's being passed to the column. So the data gets split up that way. So running this, it's going to split my data set into 4 parts now. So I have train features, train labels, test features, and test labels. So for the Boston data set, we're going to use the input columns that we picked from the feature selection process. To answer your question, Septap, this case we're using Indus, but from my understanding on what I explained till now at least, we should technically be using LSTAT in this case. So please do go ahead and try out LSTAT 2 on your machines and see if that gives better results. Yeah, so from our analysis, we picked 4 input columns and our output column is going to be Medv only. So we're going to repeat the same process. We know that these are going to be the features, these are going to be the labels, run it through the same process, and our train and test data has been split too. So based on the simple feature engineering, feature selection exercises that we did till now, we have 2 data sets that are ready, the Iris and the Boston data sets, with the features, label, train, and test already split and ready. So the data is already in place to be fed directly into a model and to get predictions out of it. So since we saw the Iris data has species as the column we want to predict, this will be considered a classification problem. Boston has Medv as the value we want to predict. That will be a regression problem. In this section, I'm going to show you a classification example, a regression example, and 3 different models each on what existing functionalities we can use to be able to classify a given data set. So the 3 different classification models that we're going to check out in this exercise are naive Bayes, decision trees, and random forest. One more thing to note, and I'm reiterating, is we will not be trying to understand what's happening inside the model. We have a separate series coming up for that. We will just take a look at how to get this model running. Are there parameters we can edit? And what these parameters mean, and trying to edit those parameters too. But to get a good understanding on what parameters do in models, it's definitely required to have an understanding on the math behind the model. Or else you're just going to be changing values based on what output you're getting from the test data, and that's not a good process for a data science project. So these are the 3 classification models we'll be using for this exercise. Under each section, I would have linked the documentation for the function that we're using, for the model that we're using, in case you want to like change or play around with it. So the first one we're going to see is Gaussian naive Bayes. The links will basically go to the Python documentation, the sklearn documentation for the model you're trying to learn. And these are like possible parameters you can pass and attributes you can pass to the model. And each of them will basically differ and make a difference in the way your model is executing and the way in which your model is producing results. So parameters are very important. If you do not have an understanding on what a parameter does, it's not a good idea to try out changing the parameters. So try to get an understanding first before you try running it. So from the cell, one thing I want to show you is this is a structure that most models in sklearn uses. .fit basically takes in the training data that you would like to predict on and fits your data into a formula that it thinks might be right. And once that's done, .predict, basically using the thing that it has learned, it will make a prediction based on that. So I think I have a question here. So what is the difference between parameters and attributes? So let me move back to this one. So the attributes, the parameters can be changed externally by us. And these are like making changes on the parameters to the model. That is what the model uses itself in general. So Gaussian naive Bayes uses priors and smoothing. And there are multiple, this is an example where it has only 2 parameters. Usually it has a lot of parameters. So parameters control how the model runs. Attributes control the data that's going into the model. So this is basically restricting the number of training samples in each class I want to provide, the probability of each class. So you can restrict the data that's being fed into the model to using attributes. I hope that answers your question. So moving back to this. So .predict would basically predict on the rows you would like to predict. So .fit will take input as your features and labels. And .predict will take input as your test features and produce predictions for that, produce the test labels for that. So this we would have to compare with test labels to see if our model is predicting well. So let me start off by running this and showing you what to expect. So usually this is running fast. Usually models take a lot of time to run because it has to compute a formula based on all of your input data. And in this case, our input data has only 500 rows and 4 columns, so it's not a heavy data set for it to run. So it ran it in basically a second. But if you see your data, if you see your model running for more than like 10 minutes or 20 minutes, it's normal. It's just that your data set is very heavy and it's taking time to make an inference on your data set. So now that I've created a model, my GNB has the model inferences trained in it. And then I'm using the same GNB parameter, GNB variable to do a predict using my test features. And this is going to be my test labels, which have been predicted. So based on this, I'm just going to run this. We see 3 labels are being produced, 0, 1, and 2. And from the iris flower data set, we saw that it's either setosa, versicolor, or other. And so we have an array of X rows, which is the prediction from the model. We also have an array of X rows from our input data, which is the actual values of the model. So we have the prediction and the actual. Our goal is to combine them both and see what happens. So you can also, like you can get the prediction, which is the values themselves, as well as you can get the probability associated with it, because this is a naive-based solution. And each prediction comes with a specific probability or confidence associated with it. So this will give you the predictions. Usually the probabilities can be used in multiple different ways. One is you can threshold your probabilities. If my model is predicting with only 80% confidence, that is when I will take the prediction it gives. So a lot of things can be done using the prediction probabilities themselves. So running this, it gives an array of the same length where each one corresponds to the probability of this prediction. This is the probability of this prediction and so on. So I'm going to put these two together so that I know which prediction has what probability, and seeing that our first row is predicted as 0 with this much probability, second row is 2 with this much probability, and so on. Running this, this thing, what we want to do is we're doing the reset index. It changes the index values of the data. And I want to put the values from my input, which is my species themselves, the species column, the test labels, that is, my train labels, which is GNB prediction, and my train probability. I want to put all these together so that I can compute some metrics on it. So this basically does that, where it just takes the column from there and adds it over here. Again, I would like to stress, please remove the join axis. I don't know why this is throwing an error in this case, but it seems to keep throwing an error. But in this case, we see these are the actual values of the column, this of the rows. This is the predicted value of each row, and this is the probability associated from this. So from first glance, I can see that my first prediction is right, second prediction is wrong, third is right, fourth is right, fifth is right, and so on. But when you have like really big data sets, it should be a non-manual process for you to know what your accuracy of the model is. So we will get to that soon. So what I'm going to do is we're going to run 3 different models because we want to know how to compare models. So the same thing applies for these 2. These links will give you ideas on what parameters and attributes are present for each of them. And I'm going to repeat the same process. And I'm going to get these columns, these 2 columns from each model, which is what the prediction is and what the prediction probability of each model is. So this basically does that. So we have a decision tree one for that too. And I'm going to concatenate it back to this one, back to our table, so that we have, this is our actual value. This is the first model prediction value. This is the second model's prediction value. So same way, we're going to try out another model, which is logistic regression. It uses linear regression. It uses regression to be able to do a classification. So it produces a class probability, even though the name says regression, it does a classification. So moving back to this, so we got the log R prediction and probability. I want to concatenate that back too. So let me just remove this parameter. Yeah, and so now we have 3 different models and the probability associated with each of them. So one thing to note over here is you must be wondering, why is this only 0 and 1 and why aren't there probability values associated with it? So that the reason for that is that's how decision tree works. It's either yes or no. There's no, I have only this much confidence on it. So it's either 100% probability or a 0% probability. So I would encourage you to look up more on what decision tree does. So Catherine, to answer your question is, aren't these accuracy probabilities really small? Does that mean it's a good or bad accuracy probability? So from this example itself, if you see, these values seem to be pretty small in comparison with these values, or at least just the first row comparison is very small compared to the value you see in log R probability. That means your model is saying that this is the class, but it isn't too sure about it. It's saying that it might be a bad one too. So yes, to answer your question, low probability is bad, and you should definitely ignore the low probability ones in your prediction. Hey, Patricia, thank you for that link. I'm just going to send it over in the chat too. So guys, Patricia shared this link on why my join access isn't working, because it's been deprecated and reindex is being used instead. So take a look at the link I've just sent on our chat and see how to integrate that back into your code. So the parameter would be a reindex instead of it being a join access. Thank you so much, Patricia. So Catherine, we still haven't gotten into the part where we are going to evaluate if your prediction probability is good or not. So in this case, you see that it is predicting the right class correctly, but with a very low probability. So there are accuracy metrics and everything in place, which we'll be jumping into soon, so that your answer should be, your question should be answered then. Okay, Patricia, I hope one of our panelists might be able to help you out with the runtime error you're getting. Do reach out to them on our chat as well as Slack and get it working. Yeah. Okay, I'm just going to close these questions. Okay, so moving on. So now we have our classification problem. For 3 models, we have the prediction and the probability and the actual values present. So I'm going to do the exact same for the regression models that we have. So we've picked 3 regression models, which are linear regression, SVM, and random forest. And we're just going to quickly run these to get an output similar to this, where I have the actual MEDV, my linear regression prediction of MEDV, and probability. Do we have probability? We do not have probability actually, and so on. So as far as regression goes, there's no probability associated with it. Since these 2 models here, which are the naive Bayes as well as log R, internally use probabilities for making predictions, that's the reason we're able to get probabilities for this. In the case where decision tree doesn't use probabilities internally to generate predictions, we do not get a probability out of it, but a value that looks similar to a probability. And as far as regression predictions go, we do not get a probability associated with it, but a specific numeric value associated with it. So I'm going to run this. So if you see, all of the models use the same format: dot fit of features, comma, train features, comma, train label, dot predict of test features will give you the predicted test labels. And then you basically join together all the data you have to make sense of it. So I'm quickly going to breeze past this. So, and join it back into our data. Just going to remove this. So we know that this is the MEDV value, and from linear regression, these are the values that we are predicting for those rows. So I'm going to do the same for random forest too, and concatenate that back into our data, and do the same for support vector machines too. There's documentation for all of them. If you'd like to know more on what these models are doing behind the hood, I encourage you to check it out and see what's going on. So I'm going to do a quick run on the SVM and concatenate that back into our results. And I'm just going to remove this since it's deprecated. So from our classification model, these are the results that we have. So we have the actual value, which is MEDV, our linear regression prediction, our random forest prediction, and our SVM prediction. So moving on, performance measures. So depending on the type of solution you have, whether it's classification or regression, there are different ways for you to analyze the model. So I'm going to quickly breeze through this and not jump into too many details regarding why confusion matrix or why this or why that, but give you an idea on what accuracy metrics are used and what is useful. And I would definitely encourage you guys to go in and take a look at what exactly each of them does to get a better understanding on it. So let's take a look at classification performance measures. One thing to note is classification, we have the prediction as well as the probability associated with it. Regression, we have only the prediction associated with it. So as far as the classification problem goes, we construct something called a confusion matrix. And this confusion matrix is used to devise whether the values your model is producing is good or not. So take this confusion matrix over here as an example and say that my data set has a column which I'm predicting, which has either 0 or 1 as the value, which is either positive or negative. You construct a table which has actual values as the columns and predicted values as the rows, and add in the counts of values right here. So in this case, I'm going to count the number of rows where my actual value was positive and my model was also predicting as positive. And sum them all up and throw it in here, where the number of rows where actual values are negative and predictive values are positive, add that all and throw it in here, and so on. So this is what a confusion matrix is. And these are a way to analyze why your model is doing badly, if it is. So in this case, we have true positive, false negative, true negative. And when you're going through any like machine learning website and all of that for classification problems, and you're debugging why your model isn't doing well, this will be the starting point which most of the websites recommend on analyzing what quadrant is your model doing well or worse. Is there some quadrant you can increase on? So false negative is wrong, you need to start focusing there, and so on. And how do you start focusing in a quadrant without it affecting the other 3 quadrants too much? And those are like important questions that you need to ask. So yeah, so this is a little more metrics that can be generated on your confusion matrix. So this is the confusion matrix that we have. And these are metrics that we use in general in machine learning for this. So accuracy is just based on the overall accuracy. It counts how many of your predictions are right divided by total number of predictions. We also have other parameters that are defined, which are useful in specific cases, such as sensitivity, specificity, precision, and negative predicted value. An example is precision is very important if you're dealing with skewed classes, because one class can have very high number of value. The accuracy can be very high, but still it might be doing really bad for the smaller classes. So precision and recall are very important in that case. And in this case, we're going to, there's like more definitions on what accuracy, precision, recall, and F1 score are. And these are the parameters that we use. These are the validation methods that we use in general to get an accuracy metric on our data. ROC and AE was also a very important one that's being used, and do take a look at this link to get some visualization on your data, on your predictions, to see if it's doing well or not. So I'm just going to, we're just picking arbitrarily accuracy as the performance metric we want to go with. Since we know that our data is not skewed, it has like a 33, 33, 33 distribution between the 3 classes that's there. Accuracy will be a good value to measure the probability for this. So here is the prediction matrix that we have, where we have the actual value, each prediction, and the probability associated with the prediction. So my goal is to get accuracy, 3 accuracy metrics on the GNB, DT, and log-R prediction, and see which one is doing best. So in this case, what I'm going to do is use this existing functionality that's present from sklearn, which I've imported initially. And it basically takes input as the actual values, which is present in our table, and the prediction values. So this is going to run, and this tells us that 93% of our predictions are right. And we're going to do the same across all 3 models. And in this case, you can see our log-R seems to be doing best, giving us 96% accuracy. And decision tree seems to be doing worst, giving us only 90% accuracy. 90% is still really high. But in this case, it's doing comparatively bad. And iris dataset is an easy dataset to make predictions on. That's why the values are so high. In real life, you will not see such high values ever. So I'm going to do the same thing for regression. But first, let's see what are good metrics for regression. So in regression, we know that the prediction is not a categorical value, but a numerical value. So our actual values are going to be numerical in nature, say 10, 20, 30. And our predictions are going to be numerical in nature, say 20, 30, 40. How do we compare these two? So there are a couple of metrics that are widely used when it comes to regression models. The first one is mean absolute error, which uses this given formula to see the absolute error of your data. And all it does is it gets the difference between your prediction and your real value, takes a mean of it and averages it out. So you know on an average, your model will be this wrong. So if my MAE value is 0.05, my assumption will be on an average, my model will predict with a plus or minus 0.05 confidence, plus or minus 0 point confidence on my data. So that is mean absolute error. And then we have a thing called root mean square error too, which is like more sensitive to outliers. MAE is not as sensitive to outliers and might not be good. And moving back to our root mean square error, this is another metric that can be used and is highly used because of its low sensitivity to outliers. R square is another method too that can be used. Adjusted R squared is one too. Since there are so many different accuracy metrics you can use, your question would be, why are there so many? Why isn't there one standard one to use? So the answer to that question is all of these are standard functions to use. And completely dependent on what kind of data you're providing, you should pick one of these based on that. Does your data have a lot of outliers? Then pick RMSE. Does your data have a lot of not outliers? Pick MAE, like that. So you have a lot of different functions to pick from, and it completely depends on the data that you have. So moving on to the same thing that we did with our classification, I want to get numbers on how well the model is doing in regression. We have 3 models to compare. And this is the data set that we're going to be comparing. So I'm going to be checking out the mean squared error. You can also try out and see what the RMSE and the functions for RMSE and so on are, and use that. That'll be a good exercise for you to try out. So coming back to this, my mean squared error, I'm just going to print all 3 of them. So from this, my understanding is logistic regression, linear regression always gives me a prediction that's plus or minus 53 from the actual value that's present midway. So our goal would be to reduce this and to make it as small as possible so our predictions are as accurate as possible. So as far as classification goes, maximizing accuracy is what we need. As far as regression goes, minimizing the error is what we need. So in this case, our 3 models basically have a 53 error, 62 error, and 74. So from this, we can say that we can confidently say that linear regression is doing way better than random forest and SVM. And it's reducing our error by 10. And that's a big value. And since our data is pretty straightforward, linear regression is working well. And mostly in a lot of cases, when you see linear regression is a really good model to run because it makes very simple deductions on your data and gets you the output that you need. So this is as far as accuracy metrics go. An exercise for you at this point would be to try out different functionalities that are present other than the mean squared error. We quickly saw that RMSE, R square, adjusted R square are other functionalities that you can use for this. And I would encourage you to try them out too and see if mean square error says that linear regression is best, but RMSE is telling me that random forest is best. What do I do? And so on. So this will give you an option to like generate more questions on your data, being able to understand your data better and so on. So next part we come to is we found out how to create our model. Okay, there's some questions. So Adiola, why is the values different from yours, the MSE and RMSE? So the way the model is built might be making that a difference. Even for me, from each run, the output is different because each time it does a fit, and during that fit, it generates a different formula every time. So even though the data is the same that's being provided, there'll be small changes in the formula that it generates to fit your data. and that will give you small changes in the output, and in the end give you small changes in the RMSE and MSE values. So if you see these things, before I ran it, they had way different values down here. But then once I ran it with my new fit, it's giving me different values. So that's the reason for that. And Patricia, I hope the panelists have been helping you out with this, and you should get it working. Okay, so moving back to this, so model tuning and optimization, we saw that we were able to build 6 models, 3 classification, 3 regression. And now we want to see, is it possible to build a better model in the same type? And in this case, I'm taking the example of logistic regression that we built for our classification problem, which is our iris data set. And this was the 3rd model that we built, log-R. And so I want to see if I just quickly scroll back, we saw that log-R was giving us the best predictions. So what we want to do now is see if we can improve those predictions in log-R by changing the parameters that it takes as input to the model building. So in this case, I'm building a log-R v2, which is basically changing some parameters. And I'm going to encourage you to go in and see what these parameters mean. And you need to get a good understanding on the math that goes behind the process to understand what's going on. And yeah, so this, I'm just going to build a model which has a little different parameters from the existing log-R model that we built. And I'm going to get the predictions the same way in this format. So there's nothing different going on other than these 2 parameters that have been passed now. So that's the only difference from before. And we're getting a bunch of prediction and probabilities associated with the prediction. And I'm going to concatenate that back to our existing results. And I'm going to remove this join axis part for that. So in this case, if you see, you can visibly see the difference between log-R and log-R v2. There is one row where the prediction itself is different, and the probabilities are very different that it's generated. So the parameters that you add is going to make the model different and make it compute a different formula for your data. So let us quickly see if this is a good thing or a bad thing with the V2. So our V1 is giving 96%. We saw V2 is actually reducing the accuracy. So we have only a 90% accuracy on this. So these 2 parameters do not work well with the data set that we're working in. And so addition of those 2 parameters changed the way in which the model was running, and the predictions generated changed, the probabilities changed, and in the end, the accuracy also changed. So an exercise at this stage is to basically check out the official documentation for sklearn, which I've linked in every section, and see what all parameters you can do to change your data and change the way the model is fitting, and visibly see the results being different. So yeah, so that's a good way for you to do a model tuning and optimization. Once you find out one of your models is doing well, log-R is doing well. Now you know that log-R is doing well, but is there a way for me to maximize what it's doing by changing some parameters in there? And that is what model tuning does. And model selection is basically picking, now that you've built n number of models, knowing what metric to use to evaluate them, and then picking which one does best is the model selection method. And in this case, I've just defined a function called max accuracy, which takes this as the input, this data set as the input, and produces an accuracy metric for that. So in this case, I'm just going to quickly run this, and it's going to tell me that log-R prediction is giving me best results. If you saw before I ran this cell, it actually said GNB prediction was giving best results, and that was from my previous run. And to answer someone who had the question on why is it differing? Like each time the fit is different on the model. You cannot replicate a fit based on a previous one. Okay, so this is a max accuracy one. This is a way in which you can go about it. In this case, we had only we've built only 4 models. So it's easy for us to like go through and like quickly see, hey, accuracy of 4 models, compare them and manually do it. But in the case in production, you'll be building at least 10s and 20s and 30s of models for a given use case at a given time. And to be able to quickly evaluate and see what's going on, this would be a good function to use. Say you have like 30 models and you don't have the time to like manually go through them. This would help you out with that. So moving on. So we saw what the maximum accuracy is. And the exercise here is to write something similar, but does it on regression. We saw how to get a regression score for each row, mean square error for each row. Being able to see that across each one would be the best way to go about this. Another thing that can be added as a parameter in this accuracy calculation is you can, one thing that I would change in this is just create it as max and take a parameter which mentions what is your accuracy metric of choice. You can pick recall or sensitivity or accuracy and so on. And changing what this row does based on that parameter is a great idea. So this will maximize the functionality of this one function to get you results on all your data. But yeah, so this is the last exercise of the session and would be for you to replicate the same with data, with your RMSE and regression values. Perfect, awesome. So this is pretty much all we had for today's session. I'm just going to quickly go over everything that we went over so that you have an idea on what all we've covered. So we saw how to load the data sets from sklearn, and then we saw why splitting data is important and how to go about splitting your data. Then we saw feature selection and engineering, what is cursive dimensionality, why is it a problem, and how to solve it. So we saw how to engineer features, select features, and whatever processes you've done till then, being able to put that into a data pipeline so you can replicate the process on your test data. And then model creation, we saw two different types. We saw the classification and regression, and in each of them, we saw 3 different types of models being implemented. So we saw the naive Bayes, decision tree and logistic regression for classification, and then linear regression, random forest and support vector for the regression problem. And once we had all the results from this, we looked into what kind of performance metrics are there for classification and regression, and how to use these performance metrics to tune and optimize your results, and how to select the final model that you would like. So there's a question here. Is cross-validation done while training and split, or at the end with scores? What is the difference? So cross-validation is a concept where you build your model on multiple slices of your data. So say I have a data with 100 rows. Cross-validation basically first builds, and this is not time-bound data. There's no order with this data. So if I have a 100-row data set, cross-validation basically first builds a model with 80%, top 80%, and tests it on the next 20. Does a shuffle of the data, does 80% top and 20. And does a shuffle 80% and 20. This is to make sure that there isn't any bias that your model develops because of the data that is being fed. I could be providing 80% of top quality data to my model to train it, and then very low quality data for the prediction. And this will build a really good model technically, but it's a form of cheating because you're ensuring that the model going to your data is correct. So in this case, to avoid that, to avoid any bias with our data, we do cross-validation so that the model is built on multiple different slices on the data and tested on the other slices present, and gives you a more rounded value on how well your model is doing. In our case, we saw that the accuracy is 90. But then if I run this over and over again on different slices of data, I'll get different accuracies on that, say 80%, 85%, and so on. So if I do a cross-validation with 5 levels, I'm going to get 5 accuracy metrics, which I average out and put together. I think 10 cross-validation is one that's used extensively, just to make sure that any bias is removed from the data. I hope that answers your question, Priyanka. Perfect. So yeah, thank you so much everyone for joining our session today. If you have any questions at all, please use the Help Me channel on Slack and tag your question with Mini Data Science Bootcamp so that one of us can get back to you with answers immediately. You should be able to find a link to this, a link to join our Slack in the chat channel. Please do join us if you haven't joined already. We have a lot of events in pipeline, and we'll be posting about these events on our Slack channel, so you will be immediately informed if you are part of our community. And then again, I would like to really thank our sponsor, Home Depot, for putting together these events and helping us bring this kind of like awesome content to you guys and keep you guys engaged in these times. Please do retweet them. I think someone should have shared the link now. And moving on, I'm just going to leave this up so that if any one of you would like to join us, you can use this as the QR codes. You should find the links in the chat channel too. So please, if you would not like to use QR, just check out our chat and use those links to join us. And we're super excited to wrap up this session. And one important thing that I want to share with you is we have an offset session coming up. This timing was more suitable for those in US time zones. So we're setting up something for the IST and GMT time zones and something that will be more suitable for that side of the world. And we're hoping to kick this off the week of April 17th, I think, next week. And next week or the week after that, check out our Slack channel to see when we plan to get that running. And once we do have that up and running, we encourage you to like share more information on it, and do join us if you join like midway in the session and would like more information about it. And also do check out our YouTube channel for recordings of the last 2 sessions plus a how-to video. And we'll also have recordings on this session available to you by Monday. So keep an eye out on the Slack channel for the links. And Deepika has just shared our Women Who Code YouTube link. So that should contain all of the videos that we have till now. And I'm hoping to upload our video from this session to the same link. So please keep an eye out for that. Join us on Slack, and excited to have you all here, and have a good day, I guess. Thank you so much for joining. Keep an eye out for the next offset session. We also have an intro to machine learning session being planned and should have that out soon. So keep an eye out for that. Best way for you to do is to just join our Slack channel, and I will see you guys over there. Thank you so much, everyone. I'm just going to leave the slide up so that you can copy these links or use them for the next couple of minutes. Thank you, everyone. Thank you for joining.